Yes, I can start.
Hello. Hello. Good morning and namaskar to all. On behalf of Physics Department, VS College Arts, Science and Commerce, we welcome you all for today's IPA DAE CV Raman lecture by Dr. S. Kailas, sir, in association with Indian Physics Association. I request our principal, Dr. Anita Kanbar, to address the gathering. Please.
Namaskar dignitaries, respected Dr. S.K. Gupta, sir, who is mentor of Dr. S. Kailas, former physics group director BARC and presently working as INSA scientist at UMDAE Center of Excellence for Basic Sciences. IPA Secretary Dr. Kripa Mai Mahata, Dr. Vivek Parker, Mr. Raman from BARC, Subhash Naik Satam from Nehru Planetarium, and other IPA dignitaries. Our Vice Principal, Professor Dr. Ritika Makhijani, Mrs. Samita Sharma Kane, also an IQAC coordinator, in charge head of physics department, Dr. Devidas Gulwade, coordinator of the program, Dr. Sarla Ratti, all teaching and administrative staff members, all invitees and dear students. On behalf of Vivekananda Education Society's College of Arts, Science and Commerce, it is my utmost pleasure to welcome you all for CV Raman lecture series organized by Indian Physics Association. Sir, to talk about the achievement of Vivekananda Education Society's College of Arts, Science and College, it is multi-faculty college established in 1979 and it is permanently affiliated to University of Mumbai, having 2F and 12B status awarded by UGC. We proudly offer 34 programs, which consists of 21 undergraduate programs, 9 postgraduate programs, and 4 PhD programs under both aided and self-financing sections. We have a BMS and BBA program, which are approved by AICT, and there is entrance exam for taking admission in these programs. Our college has achieved notable milestones, including NAAC accreditation with A grade, CGPA of 3.26 on a 4-point scale. We also have received Best College Award from University of Mumbai, and in 2021 we were conferred with autonomous status by UGC. We have received Samajik Jani Puraskar from Maharashtra Times, Green Campus Award from Synergy, DST Feast, and DBT Star College Grant from Department of Science and Technology, Government of India. On Jagtik Jal Din in Mumbai district, our Green Club for environmental protection activities got first prize by Government of Maharashtra. And above all, in 2024, we have received prestigious Pradhan Mantri Uchchatar Shiksha Abhiyan grant of rupees 5 crore for ours is only college to receive this grant in Mumbai suburban district. We have successfully implemented the National Education Policy NEP 2020 with the help of our committed and dedicated teaching and non-teaching staff members and supportive management. We are also PRME signatory and United Nations Program for Sustainability. We follow 17 Sustainable Development Goals and we submit our reports annually to United Nations. Laboratories across all disciplines are regularly upgraded with the latest technological instruments. We have state-of-the-art library with rich collection of books. Looking ahead, the college plans to equip all classrooms and academic spaces with smart boards, projectors, and interactive tools to provide an engaging learning experiences to the students. A comprehensive digital transformation integrating online learning and advanced assessment systems is also in progress. Additionally, new student-centric facilities such as collaborative learning spaces are being planned to encourage interdisciplinary learning. Free coaching for music, cultural, sports activity, and counseling services by Westlark is provided to our students. And before I conclude, I would like to express my heartfelt gratitude to Indian Physics Association for selecting our college to deliver the CV Raman talk and Physics Department for actively organizing the same. Thank you, each and every one of you.
Thank you, madam. Now I call upon IPA Secretary Dr. K. Mahata to say a few words on Indian Physics Association.
President is also online. I'll just see. Subhrati madam, will you like to say something?
It's fine. You can say.
Okay. Dr. Kailas, Dr. S.K. Gupta, and Principal Madam, Vice Principal Madam, and Devidas Gulwade sir, Head of the Department, Physics Department, and other VES college staffs, and my colleagues from IPA, and the students. So, very good morning and very, very warm welcome to this today's Dr. CV Raman, DAE CV Raman lecture by Dr. S. Kailas. And it is a very proud moment for me. Actually, I want to show a slide because today's speaker is actually my guru, and in fact, he selected me in the training school as his, and also after the completion of the training, I joined him, and so he has mentored me all along my career. In fact, he is still very active, and whenever some paper or some work is published in this area, he always gives me a summary and maybe 10-15 questions on that paper that which are not clearly explained. And he's also very kind-hearted person. So I feel that I am fortunate that I got the opportunity to work with him. So I'll briefly tell about the activities of IPA. So the IPA is Indian Physics Association. It was founded in 1970, and the objective is the advancement and dissemination and application of knowledge of physics. And it is a very like you can see the big organizations, like you have more than 4,500 members and 48 chapters in different cities all across the India. And we have also like licensing with many national like societies of physics, and also linkage with the international societies like the American Physical Society, Institute of Physics UK, and others. So the main activities of IPA is like the publication of like one physics news we published every quarterly, that is a IPA bulletin. And this what we are doing today is like special lectures and seminars, which are like DAE CV Raman lecture series, PA Pandya lecture series, IOP, this is the International Exchange, IOP Indian Institute of Physics UK, and IPA Homi Baba Walton lecture series, which we will also do maybe in the month of April. And then we also organize like young physicists meet for the young researchers and various team meetings. And also we are like giving awards to various with various categories. So this is the like a few photographs of the IPA physics news, which you can see in this web link, and also you can write to this email if you want to get a copy of the like soft copies and hard copies of this physics news. And these are the various awards we have, like very prestigious, which are like very senior people are awarded. And there's a BM Birla Award, Murli M. Chugani Award, P.K. Iyengar Award, Hema Ramchandrani Award, SN Sasadri Awards, and so on. And also we have like for young researchers like Best Thesis Awards, and for students like CL Watt Memorial Award for the best student at the Indian Astronomy Olympiad, and IPA Award for International Physics Olympiad Awards. So this information you can get in the IPA website. This is the website of IPA. If anybody is interested to become a member, so you can just fill up the form and become member. This is the present executive committee. And IPA also have a gender in physics working group, which is also very active, and they are actually addressing various issues related to gender parity in physics profession. And this to tell about the DAE CV Raman lectures, you can see that like this is very prestigious lecture series. So like some of the names, this is like this Bharat Ratna APJ Abdul Kalam. This was our ex-chairman and PSA to the Prime Minister R. Chidambaram, and many others, like the present chairman of DAE, this present principal PSA to Prime Ministers. So, and we'll today in that we'll continue with this lecture by Dr. S. Kailas, and I'd like to thank him for accepting our invitation to give this lecture, and also I thank the VS College for organizing it on behalf of IPA. With this, I'll and thank you.
Thank you, Dr. Mahata. Now may I request Dr. Devidas Gulwani sir, in charge HOD Physics Department, to introduce our speaker.
Good morning, everybody. Today, we are privileged with the presence of renowned nuclear physicist Dr. Kailash, and also his mentor, Dr. Gupta. Dr. Kailas and Dr. Gupta's insights and experiences have shaped the research frontiers in nuclear physics. Their work led to expansion in our understanding and also paved the way for the groundbreaking advancement in science and technology. Dr. Kailas is a former director of physics group at BARC, Baba Atomic Research Center. Currently, he is INSA honorary scientist at University of Mumbai, DAE Center for Excellence in Basic Sciences. Dr. Kailas, a graduate from Madras University and PhD from Mumbai University. He has joined Nuclear Physics Division, BARC, in 1971. He has specialized in accelerator-based nuclear physics. He has nearly published 300 articles in various journals of academic repute, and has guided more than 10 PhD students. Dr. Kailas is a fellow of Indian Academy of Science, Indian National Science Academy, Tamil Nadu Academy of Science, and Maharashtra Academy of Science. He has received Sir C.V. Memorial Medal in Physics Sciences from the Indian Science Congress. He is a former president of Indian Physics Association. We welcome Dr. Kailas and Dr. Gupta and all the dignitaries of the IPA, and I request Dr. Rathi to start with the further proceedings.
Thank you, sir. We request Principal Madam, Dr. Anita Kanwar, and Vice Principal Madam, Dr. Ritika Makhijani Madam, to felicitate our guests, Dr. S. Kailas sir and Dr. S. K. Gupta ji. So Gupta sir is mentor. So as I would just like to say, Kripa's mentor is Kailas sir here, and Kailas sir's mentor Gupta sir is here. So it's a really a big day for us, sir. Please. We are privileged to have you. Thank you.
Yeah.
You are here to help.
Yeah. I can use this. Of composition.
Very good morning to all of you. I think it's actually past 12 o'clock now. I'm standing between you and lunch, so I hope you will bear with me. And after lunch, it will be anyway, you will feel sleepy, so it is good to have the talk before the lunch. I consider it a privilege to get again an opportunity. I came here almost 8 years ago to give a lecture, and I thank again Indian Physics Association and Vivekananda Education Society for giving me one more opportunity to deliver this kind of lecture. I thank the principal and other distinguished faculty members of VES for again inviting me. This program has been, I think,
Stop the sharing and share. The slide is appearing.
I'll just.
Online, that extra slide is here.
actually that should not be there.
Extra slide. Just a second.
Actually, just for your information, this program has really materialized thanks to two people who work behind the scene. One is the husband and the other is the wife. Husband is, of course, Dr. Kripa Mahata from BARC, and the wife, of course, is Salarati from VES. So they were the people who really worked and made it possible. I'm very happy to meet Dr. Gupta ji, who was one of my mentors during the formative years in BARC, and many of the things which I learned, they were all both theoretical and experimental skills, whatever I acquired, thanks to his guidance. And I learned many things by seeing what he does. So I'm very happy he's sitting in front of me today. Of course, Kripa gave a lot of praise for me, and we are also very happy that we could get bright students like Kripa and others who joined our BRC training school system. And I'm very happy he's doing very well in his professional career and wish him all the best in the years to come. Actually, a few days back, we had the National Science Day, and again, remembering Dr. Sir C.V. Raman for the discovery of the Raman effect. In fact, this is going to be discussing today. What are the beneficial uses of nuclear radiation? Nuclear radiation is an ionizing radiation, and it is arising mainly due to nuclear process. And you will not realize it is present everywhere, even in this room. The air we breathe, the food we eat, the water we drink, everywhere nuclear radiation or the effect of that will be there. But you don't have to be scared because it is in a very safe limit. And the very fact that we have been living comfortably with good health means this nuclear radiation is not harmful to us. But we have to realize this is something which is God given our nature. It is from nature. We have this radiation all the time. And this level of radiation is so small, it has not affected us in any way. As you know that low level of nuclear radiation competes with other two factors.
Someone's been sharing a stock.
Oh,
Sorry. rejoin once. Start. Just a second. Sharing has stopped. Disabled.
It freeze or something.
Yeah, somehow this sharing is not coming over. No, it is not. Okay, I have to just go to this that. Function. It's gone. It's gone.
Maybe two sides are open. Please check. Close it first.
इसको बंद कर देता हूँ.
Close this one also. This one also.
This is what you want to protect.
Yeah. First close it, then we will reopen it.
Okay.
Then we will close it, this one also.
Okay. हो गया इसको मिनिमाइज करो हो गया बराबर है मल्टीपल साइड्स ओपन था ना उसके में आ रहा था नाइस इधर भी वही आना चाहिए ना
Thank you, Raman.
Just changing or not?
Maybe I can use this. Will it work? हाँ,
अभी
ठीक है? Thank you, Ram. So as I was telling you, low level of nuclear radiation also competes with, we are all familiar with pollution, chemical pollution, and also temperature cycle, very cold and very hot. So all these three have an influence on humans. So when we say something has happened, it is not due to nuclear radiation. This is what I just want to clarify. There can be due to chemical or due to temperature cycle, and all of them contribute whenever some problem comes. So nuclear radiation consists of protons. You're maybe familiar with some of these names: neutrons, alpha particles, gamma rays. Mentioning some of them. A natural background of nuclear radiation, that things come from cosmic rays. Then you also have this construction material, which consists of uranium and thorium, and then their decay products, because they are not stable. So their decay products, radon is one of the things, decay product, which also gives alpha particles. So this is all there, like terrestrial radiation as well as coming from the cosmic rays. All of them are natural radiation, and which is there all the time and at a sort of annual level of some fixed quantity, which is safe for human beings. So we call it natural nuclear radiation. We can also have nuclear radiation produced by man, that is man-made, which basically we use charged particle accelerators or nuclear reactors. You are all familiar with X-ray machines in the dental and other places. They all give you, to some extent, the nuclear radiation. And this nuclear radiation coming from these accelerators and reactors, of course, can be controlled so that it is safe for humans. Nuclear radiation is part of nuclear physics because we are dealing with protons, neutrons, and all that. And the tools employed to do nuclear physics investigation research, you know that the charged particle accelerators, research reactors, different types of detectors. Then we use also high performance computing, then electronics. All of them put together contribute to development of technology starting from nuclear radiation science. Just to give an overview of the various major accelerators, charged particle accelerators in India, we have one in Delhi, then Calcutta, IIT Kanpur, then Bhubaneswar, Hyderabad, Mumbai, of course. I don't know how many of you have seen the accelerators in Mumbai, both at TFR and BARC. Right in Mumbai University, we have a small accelerator. Then we have at Kalpakkam. And of course, the biggest accelerator right now is at Indore, which is an electron accelerator. The corresponding numbers for the nuclear reactors we have about 24 reactors operational in the country. And last year, one was commissioned at Kakrapar. And they are all located in very scenic places: Narora, Rajasthan, Kakrapar, Kaiga, Kudankulam, Kalpakam, and Rajasthan. So there are the places. Of course, more places will be chosen for the future reactors. This is the figure from Kakrapar, Unit 4. It was commissioned very recently, August 20, last year. So coming to nuclear radiation science, of course, the main interest is in basic nature of nuclear radiation and the science with that. And then the number of technologies which can be developed using nuclear radiation as well as the related technologies. They span a range of, it could be healthcare, industry, environment, archaeology, food and agriculture, energy, and national security. So I will cover some of these topics and sort of tell you how this nuclear radiation and the related technologies have been employed in these various areas. First one is the application of nuclear radiation in nuclear energy generation, which is very important to all of us. And you are all familiar, there are two forms of nuclear energy. One is the nuclear fission process, where you have a heavy element like uranium splitting into two heavy fragments, two light and heavy fragments. The other one is fusion of two light nuclei and giving you energy. This is called the fusion energy. The other one is called the fission energy. In both these processes, both are nuclear reactions. In both these processes, energy is liberated. In the world, there are about 450 nuclear reactors which are operational, generating, I think, 30% of the world electricity. There are other forms of electricity, as you know, the coal-based, the hydroelectric, and then solar, all these forms of energy. 30% is nuclear in the world. And about 50 new reactors are under construction in different parts of the world. In India, we have right now 24 nuclear reactors and generating 8 gigawatts of electricity. Another 9 reactors are under construction at various stages, which will add up to another 7,000 megawatt of electrical. We have also one reactor coming up at Kalpakam, which is plutonium based, plutonium as a fuel. The rest of the reactors use uranium as the fuel. Now, one question may arise, why we require nuclear energy in our requirement of electricity. So this slide will tell you. As you know that India is becoming a developed country, and assuming we require a large amount of electricity for consumption for public at large, one estimate says by 2070, the per capita electricity need of our country will be about 2,000 kilowatt hour per year. So that means we have to generate 3,400 terawatt hour per year estimated, taking into account the population, the growing population. All renewable energy put together, the potential is only 1,300, less than around one third of our requirement. Out of that, again, one third is solar. So how do you get that extra two thirds? That is where comes the nuclear energy, which is also a safe method of generating electricity. So, which is also nearly sustainable, renewable. And this is an article by Dr. Sukatme. And so it is very clear, just saying that solar hydroelectric or wind power or coal-based power, they are not enough. So we have to have nuclear energy also as one of the extra methods of electric power generation. So that's what Dr. Chidambaram always used to say, that nuclear energy is an inevitable option in the energy mix of our country. It is safe, economical, and sustainable. India has the resources to build and operate nuclear reactors. India has a high safety record in running nuclear reactors. To enhance nuclear energy in a fast time scale, we are also exploring international collaboration. This is just for comparison, nuclear versus coal-based and hydroelectric. The first one is hydroelectric. In all the three cases, we are talking about 1000 megawatt electrical. Suppose you have only hydroelectric as a method, then what is the sort of disadvantage? Submergence of 2000 to 5000 hectares of land, because the water will go all over the place. If you have coal based, that is the rightmost column, land required is 70 hectares, coal some estimate, it means 5 train loads of 2000 ton each per day. So you can see the amount of coal which has to be transported per day. And burning the coal means you are also emitting to the environment carbon dioxide, sulfur dioxide, NO2, ash generation, so many million tons. So they are not good for us. Now compare it with nuclear. We require 20 hectares of land and 120 tons per year. That's all we require as fuel. So nuclear is definitely an attractive option for nuclear power generation. So let us go to the next area where the nuclear radiation science and technology have been employed, which has made a great impact to all of us, is healthcare. You know that elements are present in nature and they have isotopes. But what we are talking is radioisotopes. That means these isotopes do not exist in nature, but they can be produced artificially using nuclear reactions. And why do we require them? Because they are useful for healthcare. So we see some of the isotopes. Cobalt-60, which you are all familiar, used for cancer treatment in a big way. You know that in nature, cobalt exists only as one isotope, 59 cobalt. But 60 cobalt is useful to us, and that can be produced by neutron-induced reaction on cobalt-59. Then iodine-131, again in nature, iodine-131 doesn't exist. Then technetium-99. They are all produced using nuclear reactors, neutron-induced reactions. We also can use charged particle accelerators to produce radioisotopes, like fluorine-18, 201 tellurium, 123 iodine. They are all other important isotopes. I have mentioned only a few, just to give an example. What are they useful for? They are useful both for diagnosis and treatment. Image organs. You know that nowadays, if you go to any specialist doctor, he wants you to come with not only blood report, but also the PET scan and various kinds of MRI. So many, then only he can, because he cannot cut open the body and see what is there inside. So they want to do all this imaging. It has to be done, and very, very important for treatment. And also finding what is the illness or what is the problem you have. So image organs to determine the functioning of brain and heart. Image blood flow, glucose uptake of different organs, and oxygen consumption. Because they are all important to know which is a normal behavior cell and what is the one which is having some kind of problem. So tumor and cancerous cells absorbs more glucose than normal cells. So there is a difference. So you can make use of this fact to find out which are tumor cells and which are normal cells. Then iodine has a great affinity for thyroid. So when you put iodine isotope, it will go seeking the thyroid. And by imaging the thyroid, you can find out whether you have some problem with the thyroid. Slower washout of thallium from compromised but viable myocardial tissue as compared to normal ones. Again, the one which is having problem will behave differently from the one which is normal. So this is for a problem with the heart. You can use again a radioisotope. This is just to say that these radioisotopes, they have a finite lifetime. That means they live for a short time, and by that time the investigation has to be carried out. And you don't have to be worried because these isotopes, they are given in the form of some kind of chemicals which are good for the body for consumption, for us to consume, and they also go out in urine and other places. So they don't reside in the body for a long time. So we don't have to be scared. It is required only for imaging purpose. After that, they come out. So that half-life is very small compared to the actual half-life of these radioisotopes. So just to say that how this nuclear reaction takes place. So what we have is neutrons coming from the nuclear reactor or from accelerator, whatever, and then hitting a uranium. So it hits a uranium target, and it is split into two big fragments and two light ones, which are neutrons. So you have the iodine and yttrium. It can fragment into many ways, and this is just one of the ways it can fragment. And not only that, you have these new isotopes which are radioactive. They are produced, but also energy is generated. The other one is proton-induced reaction on oxygen 18. We have a machine at Tata Memorial Hospital for producing this fluorine 18 isotope. So here what happens, you have a proton beam from the accelerator, and oxygen 18 is the target. So proton goes and hits the oxygen and then knocks out a neutron, and oxygen 18 is converted into fluorine 18. And fluorine 18 is what we want, which is a radioisotope, which is used for imaging purpose like thyroid and other purposes. So this is the accelerator, which is located in the basement of Radiation Medicine Center at Tata Memorial Hospital. And this is a 16.5 MeV proton machine, and it can be used for producing many isotopes. Just for information, what I collected from literature, we have for medical therapy 350 linear accelerator, which are electron linear accelerator. That means they give electrons as the method of diagnosis or treatment. Then 24 medical cyclotrons, which are mainly used for producing radioisotopes. And then 200 radioisotope based treatment facility, that is cobalt. So they are not based on reactor or accelerator. So we have so many facilities in the country. This number maybe, I took it from some paper. So you can see 300 and around 600 facilities are there for diagnosis and treatment right now in the country. This is a typical figure setup. The person is here and is surrounded by, the person has been injected with radioactive isotope, say like fluorine 18, which is a positron emitter. So it interacts with the electrons in the medium and emits two gamma rays. And these two gamma rays go in opposite direction, and they are detected in this ring detector. And that is the way the imaging is done of the person. So this is a picture of the brain, and you can see the part of the brain which is having a problem. And you can see that yellow and then red color. Red color means that is the place there is a concentration of some problem of the brain, and this is very helpful for the doctor to diagnose and then plan further treatment. So this is again use of radioisotope, which is given to the patient, and then later on you image the particular part of the body. This is one of the homegrown development of technology from BARC. This is based on cobalt-60 as a radiation source, and then that is used for, as you know, for cancer treatment is one of the places, and this is one of the things which has been developed and then commercialized. A lot of units are there in the country. So the question is, these are all the facilities, cobalt and others are okay, but if you have a person unfortunate to have a deep-rooted tumor or cancer, then this method will not be as effective. So in that case, one goes directly for use of high energy protons from accelerator. And only recently, India has been able to get this kind of machine. One is at Apollo Hospital, Madras. Other one is available at ACTRAC at New Bombay. Both are accelerators which are going up to 250 million electron volt energy protons. So the proton is directly injected into the patient having a deep-rooted tumor or cancer, and this proton beam goes and hits that tumor, and then that deposits that energy towards the end, and then it is like heating. It is like when you deposit energy, that local area gets heated up, and that way the tumor is destroyed. And the main behavior of high energy proton is normally X-rays, when you enter the body, the tissue or cells, they affect the beginning portion more than the end portion. Whereas the high energy protons affect the portion at the end and less the beginning. So there is a contrast between the two. So when you want some problem to be treated deep inside, then the high energy proton is the best method. When you want to treat something closer to the skin, then the cobalt and other methods are quite good. Anyway, these kind of facilities are available now in the country. So you can see that this is a tumor, and after treatment with proton therapy, 6 weeks after treatment, you can see this is gone. So this kind of facilities are available now in the country. And this is so you can see this is where the proton beam comes. This is a huge gantry which is rotatable. And the patient is sitting here or lying here. And then it can be rotated and direct onto the patient, whichever part has to be irradiated. So it will be a small pencil beam type of thing, and a lot of work goes on before the treatment starts. And this, as I told you, this kind of machines are there in Apollo Chennai and ACTRAC. One of the areas where nuclear radiation has been used in archaeology, just one example I'll give, particularly in museum in France, they have a mini accelerator located, and also in Italy. You can also use radioactive source. So what is done is you put the radioactive source, and this is a painting or something in the museum. You irradiate with the nuclear radiation, and then you excite the molecules or the pigments in the painting, and that the pigments consist of various elements. So by measuring the characteristic X-rays getting emitted, you will be able to say what are the elements present in this painting. So you know that forgery and other things take place. Somebody sells something which is as original painting, but then by doing this kind of thing, you will be able to find out what are the elements present in that painting without destroying the painting. You cannot destroy the painting. So you have to do in a way the painting is not destroyed. So you use the radioactive source to excite the elements and then find out the elements which are there, whether these elements are of the old, whatever things which people were using, say, centuries ago, and how do they compare with what we use today. So it is possible to do this kind of thing more like forensic science. One can do all this with nuclear radiation. This is just one example. In industry, of course, this is one of the biggest application of nuclear radiation today. Ion implantation. Here we use very small, low energy accelerators. As you know that this semiconductor industry nowadays, for changing the conductivity of semiconductors, they have to put various elements like boron and others in various amounts to change the conductivity, and it is all done using ion implanter. Maybe 10, 20, 30,000 units are there in the world, mainly for doing this ion implantation. We have one small facility in BARC also. So one of the largest places where small accelerators and nuclear radiation is used is in ion implantation or semiconductor industry. The other one is using electron beam. You can do material processing. And you can see here, I don't know how clear it is, between two, this is a polymer and the electron beam is coming here. And you can see these two polymers are getting attached. So this is what we call cross-linking of polymers. So why it is required? By doing this, you can change the property of the polymer and make it more strong and also have better mechanical, thermal and things like that. So this has a lot of application, and one of the things is using this cross-linked polymer, which has more strength than the original polymer. If people have even used it for substitute for copper piping. Instead of metal, you can use this kind of plastic-like substance. Electron beam irradiation also has been used, again, for changing the property. Some kind of rubber and other things, if you use this electron beam, again, that property changes. And I don't know how many of you have heard, we also have something called heat shrinkable tubes. So what they do is when you join two pipes, they put as a sleeving this kind of heat shrinkable tubes, and then you heat it. Instead of the rubber melting, it shrinks and binds these two, as a nice joint between these two tubes. So this is called heat shrinkable tube. In the cable industry, they use it in a big way. So heating the rubber or the plastic-like substance, it doesn't melt, but it shrinks and then holds two parts together. Then sterilization of medical products, which is one of the important things. All the medical products are packed in cartons, and then they go through radiation source like cobalt, and then they are irradiated with some amount, and then the pathogens and parasites, they are all taken care of, they are killed. So sterilization of medical products, I think in BRC we had it more than 50 years ago, and it's still that unit may be working. Removal of toxic waste. As I told you, in these coal-based plants, you have this toxic gases, fly ash and other things, which consist of sulfur and nitrogen compounds. So how do you get rid of them? Again, you can use electron accelerator and convert this sulfur and nitrogen into some kind of sulfate compound, nitrogen sulfate compound, and then remove the good amount of sulfur and nitrogen from this fly ash or flue gas from the coal plants. This also has been done, but we have done only demonstrated this in BRC, but we don't have still an operational facility. But in some countries, they have it. Of course, we have other methods of controlling this pollution, but this is also an effective way of controlling this nitrogen and sulfur pollution. Radiography, you are all familiar, inspection of wells and other things. This is just, I don't know, yeah, sorry. Anyway, you can see that one side is the radioactive source, other side is the detector, and in between you have this liquid or whatever is put in between, and if it is moved, then depending upon the absorption of this radioactive source, that gamma ray or whatever, then you will be able to say whether the sheet is uniform or non-uniform. If it is non-uniform, the flux coming this side to the detector will keep on changing. If it is uniform, then what is measured in the detector on the right hand side will be same throughout. So uniformity of sheets can be checked, and also the flow rate in process industry can be controlled by this kind of devices. Another area which is again important is agriculture, where radiation source has been used. And this is a picture from Maharashtra Amravati district. They have used some radioactive isotopes, basically to find out the groundwater sanctuaries. You know, some of these areas, they are starved of water, borewell has to be dug, so we don't know where to do it. So one can use radioactive isotopes as a tracer. You know, it will go to long distances. From that, you will be able to find out which is the more likely to be waterborne, where water will be more easily available. And this kind of technique, BRC has a mastery over it. So this has been employed, and you can see that the top figure, the sort of barren land without water. Then once they found out the water bodies, they could use it, and you can see that it has become very fertile. So this is one area where in agriculture, this radioactive isotope has been used very effectively. This is another area where BRC has done good work over the years, is to irradiate seeds or plants and make it undergo mutation. See, mutation is taking place even in nature, but using radiation, nuclear radiation, you can accelerate this mutation. And why do you require it? Because you can change the properties of these plants or seeds. And you know that if you go to a farmer, he will say he wants a seed, which, the yield should be, instead of 3 months, it should happen in 2 months, and it should be growing without much of water. It should not be affected by too much rain or too less rain. He has a big list. So normally the normal seeds, it is not possible to satisfy all this requirement, but the seeds which have been artificially irradiated or mutation has taken place in these seeds, they come with very good properties, like high yielding, early maturity, drought tolerant, resistance to biotic and abiotic stress, temperature or pollution, all kinds of things, it should withstand the stress. So this kind of things, groundnut in Maharashtra, I think good percentage is using the seeds developed in BRC using this mutation technique. And I think maybe 70-80% of the groundnuts in Maharashtra is all due to BRC. There are a number of products which have been released to public and agriculture. I think more than 40-50 varieties over the years. Another area where this nuclear radiation has been used in the food industry. We understand, you are all familiar that we don't have, even though we may grow large amount of food grains, we don't have proper place to store them. So many a times they go waste or some in the rain or something like that. So 30% of, some estimate says 30% of food and fruit spoiled due to improper storage facilities. So the question is, can we extend the shelf life of these food products? You are all familiar, you buy potato from market and or the onion from market and then don't use it for a week. You know that sprouts come in that. Then you have to throw it. So is there a way I can inhibit the sprout growing? So there is an answer. You can use a nuclear radiation, treat the potatoes and onions, and then the sprout instead of coming in 1 week, maybe it will come after 1 month. That means to that extent, up to 1 month you can have without any problem. This has been achieved, and we have facilities in the country where you can treat these onions and potatoes in a bulk, and then you can extend the shelf life. Of course, you can do this delay in ripening of fruits. You know that people who are selling fruits in 2 3 days, it decays. So if you say that fruit can stay there fresh for 7 days, to that extent, the person will be very much benefited. You can also irradiate cut flowers. Suppose the tulips which are available in, say, Kashmir, if you can irradiate and extend the shelf life, then just like Holland, they send tulips all over the world. We can also export tulips from India and go to other countries. So we have to basically extend the shelf life of the food products. It could be flowers or vegetables or fruits. It's all possible. Many things have been done in the country. Of course, it is also known. Even the spices can be irradiated. You know that in the house, again, if you keep it so the besan and other powders, after 1 month, the insects come. So, by if you irradiate, then you can extend the shelf life. And it has been certified. All these irradiated food articles, it could be fruits or flowers or vegetables, they don't contain any radioactivity. There is a misconception. See, suppose you have a potato there, I'm using something to irradiate. It is like heating that, from a remote. It doesn't have radioactivity going into that. Just like, you're heating something in a box or putting a chemical around there. You know that people use chemical to delay the ripening. But they are all dangerous. If you don't wash the fruits, then the chemical also will be there. But whereas the nuclear radiation, it is like heating the things from a distance. And there is no radioactivity in the product. Always there is a misconception. They think that the food irradiated is radioactive, which is not the case. So it is safe for human beings, and it is not only we say this, but internationally accepted. So we have a lot of radiators, and you can see the sprout inhibition. And many years ago, we exported large quantity of mangoes to United States because they said unless you irradiate, you cannot send it to United States because you have to kill the pathogens or insects which are in the seed of say mango. So they have to be irradiated, and then we could send it abroad. Other important area is national security. Again, how nuclear radiation is used. So you can see that we have an electron accelerator giving you gamma rays or X-rays, and the consignment was supposed to be only wooden logs. But suppose somebody has hidden a motorbike in between, as you can see here. So if you do the imaging with the X-rays, you can see that because the absorption is different from wood compared to the metal like a bike. So doing the contrast imaging, you can find out a motorbike has been hidden. So this is something, you cannot open every container and remove every log and to find out whether something is there or not. So you have to do the interrogation from outside. This is a requirement all over the world. You have so many containers going from one country to another country, and it is humanly impossible to open the container and examine every product. So everything has to be done remote. That is where the radioactive source are very much used. This is one of the things which worries all of us, the explosives and illicit drugs. These compounds have predominantly oxygen, nitrogen, carbon, besides hydrogen. So they have different amounts of nitrogen, carbon, and oxygen. So if you can find out a particular compound has so much of carbon, nitrogen, and oxygen, there is a table available to us. For instance, here, ammonium nitrate has so much of hydrogen, so much of nitrogen, and oxygen. There is no carbon. Like that, various compounds have different amounts of these four elements. So if you somehow find out how much is each of this, and looking at this table, you will be able to say which is that compound. You know that many times you say that in airport or railway station, somebody has left a bag and gone, and you don't know whether it is safe for somebody to touch it or not. So immediately the police brings it to some lab. Many times they have come to BRC also, saying that please tell us whether what it is. So what do you do? So you have to do some kind of interrogation and find out what is that substance. And so this is very important to know. For instance, nitro explosive like nitrocellulose. This is the composition. This is another RDX. This is the composition. You see, they are all different. Cocaine, morphine, they are all having different amounts of carbon, nitrogen, oxygen, and hydrogen. So if some way you can find out this composition, then you can look up and tell whether it is RDX or cocaine. So this is what is to be done. So how do you know how much of carbon, nitrogen, and oxygen are present in that compound? So that is where you use the nuclear radiation. So you can use either very low energy neutrons or fast neutrons. So what you do is you have the low energy neutron hitting the compound and it gives gamma rays due to nuclear reaction. And from measuring this gamma ray energy and intensity, you will be able to say whether the gamma ray has come from interaction with carbon, nitrogen, or oxygen present in this compound. So you can see here, nitrogen in air, of course, we have. So this much is background. The reddish graph is with explosive present. So you can immediately find out that it is much more than the background level of gamma ray, and it is due to nitrogen, which is an explosive part of the explosive. You can also use fast neutrons. So what you do is you have the neutron generator, you have detectors above and below, and this is a suitcase containing the, say, suppose explosives. So if you have no suitcase, this is the one. This is a spectrum of gamma rays if there is no suitcase, the red color. As soon as you put the suitcase containing, say, explosives, then you have this kind of spectrum. This is coming from oxygen present in that sample. This is due to carbon present in the sample. And then if you subtract this background, which is there all the time, from this, then you get this kind of signal. So immediately you can see there is something due to carbon and there is something due to oxygen. So you can quantify how much of carbon is present and how much of oxygen is present in the explosive put inside the suitcase. And then once you know this, then you can go back and see what is this explosive, whether it's a TNT or whatever it is, RDX. So you are using either slow neutrons or fast neutrons and carry out nuclear reaction, and the gamma rays are emitted from the nuclear reaction, and that they are characteristic of the element present in the sample. So to sum up, doing basic research, which we do most of us, keep in mind how to use this knowledge for development of technologies which will benefit the society at large. Today's science is tomorrow's technology. Nuclear science and related technologies have profound influence on society, and we have gone through some sectors like energy, healthcare, food and agriculture, industry, and also, of course, security. All these areas are important. C.V. Raman said once, success can come to you by courageous devotion to the task lying in front of you. In DAE, we have this is the last slide. In DAE, a number of these technologies. So those of you interested, you are staying very close to BARC. I'm sure some of you have your parents or relatives, friends working in BRC, and definitely you can find out a way to enter BRC to see some of these technologies developed in-house. As India becomes a developed country, increased use of nuclear radiation will be there. A training, why do you have to know all this? A training in nuclear radiation science and allied technologies will open up opportunities for you for a career in nuclear power program, where we want large number of people to be part of it, because we are going to build more and more reactors. Healthcare facilities, again, a knowledge of nuclear radiation is very important. Medical instrumentation, semiconductor industry, companies making nuclear instruments and detectors. So once you have some exposure to nuclear radiation science, you will be useful in many of these places. So you don't have to worry about your future, particularly your professional career. Some of the references, those of you who would like to know more about some of the things which I discussed. Accelerators for Science and Society, Current Science, there's a book. So a number of references, it is only a partial list. I would like to end my talk by dedicating this lecture to the memory of Dr. Chidambaram, who is one of my mentors, who passed away in January. In fact, it was he who approached the Department of Atomic Energy almost 30 years ago to fund a lecture series, the DAE C.V. Raman lecture, what we have today. It was his initiative to get Dr. M.R. Srinivasan was the chairman of Atomic Energy at that time. He approached him and got funds. He was director of physics group that time. He got the funds for this DAE C.V. Raman lecture series. And he used to say that research involves generation of new knowledge, while innovation requires adding economic value to the knowledge. So, we say science and technology are two sides of the same coin. And when we're doing science, we should be aware also of the technology which can come out of it. Thank you for your attention.
Thank you, sir. Yes. Yeah, thank you so much, sir, for enlightening us with such a talk. Like, you have covered accelerator map, nuclear power plant, application of nuclear radiation, like health sector, Babatron, hadron therapy, and medical cyclotron. Also touching upon archaeology, industry, like semiconductor industry, agriculture, food irradiation, and also on national security. Sir, we are very much thankful to you for this enlightening and enriching section on nuclear radiation and its isotopes. I call upon our Vice Principal, Madam, Dr. Ritika Makhijani, to, as a token of appreciation, please give a memento. We call upon IPA members. Please, IPA members, please come on the stage.
Vivek, come.
Yeah, I'm very happy to get from a very great.
In our college, sir, we instead of giving flowers, we plants.
No, it's nice pleasure for me.
Thank you, sir. The session is open for discussion. If you have any questions, sir, you can sit. Students, you can ask questions. So just to, I mean, a little bit of information. These students had been to Homi Bhabha Science Education, HBCSE 3 days ago. Then they went to TIFR. They visited Peloton Accelerator and many more facilities.
Oh, very good.
And some few students, only 15 maybe from TYBSE, they could get an opportunity to go to BRC on a open day, this National Science Day.
Okay.
And with your talk, I think this year was a very great achievement for them.
Yeah.
They could learn so many things.
No, you can
So
do also sometimes projects in BRC.
Yes, sir.
I don't know, Dr. Kripa Mahata and Vivek Patel, Raman Saigal, they will tell you what are the opportunities available today. Because we want young students to be part of our program.
Yes.
We otherwise we are the only people, and only recently we have recruited large number of students, junior research fellows in our system. And how do you do so much of program in the country unless young minds like you become part of it? So we have to attract young minds like you to our national program. And one way is you have to go and see. Then only you will get impressed. See, the purpose of giving this lecture is to say what is all there available to you. So you may not be aware of opportunities we have in the country. Whatever I have told you is only a bird's eye view of what is there. But much more is there, and only when you see it, just a PPT, PowerPoint projection, it will not tell you everything. But when you go and see a proton accelerator at ACTRAC, then you will see how gigantic it is. So all these things are available in the country, and you are the people who have to make best use of them.
Yes, sir. So we do send some few
Yeah,
students.
no, I'm sure you are
Yeah,
doing
yeah,
it. I
yeah.
appreciate
Thank you,
it.
sir. Yeah. The session is, if students you have, please ask questions to sir. Or online Zoom, you can, in Zoom, online if you have any questions.
Any particular thing? Just of course, more things you can definitely talk to my colleagues from BARC. Something which excited you or which bothered you during the lecture?
Sir, I have small questions to you. I'm here.
Ah.
How did you yourself got influenced to get into the physics?
Physics. Of course, one is Dr. Chidambaram himself. And, I was doing my school when we got married to my aunt. So I had Hello. No, I was fortunate to have Dr. Chidambaram in our family. So, I got influenced by being there in the physics faculty. So I took up physics. Of course, even though I wanted to do engineering, but then I at some stage decided to do physics. So in some sense, he was influencing my decision.
Thank you, sir, for such a nice talk. I have a small question regarding the proton therapy. Like when we say that we have to burn the tumor at particular point, So do we have to change the energy of this incoming proton and lot of calculation needs to be done very in advance?
Yeah.
Means lot of calculation needs to be done, and then only we can get that particular energy.
Yeah.
And how that thing is done, like how do I know that I have to give this much energy now so that it can burn that particular bit?
See, this proton accelerator is variable in energy from 70 MeV to 250 MeV. So if you plot that curve, whatever I showed, for different energies, then you can see that it is peaking at different depths. So depending upon the where the tumor is there in the body, they will choose the energy.
Means we have to first determine the tumor location.
Yeah, sure. First you have to locate the tumor. Lot of work goes and I don't know, but I read somewhere some the IBA is the company which sells this kind of medical therapy machines. I think 5 lakhs or 10 lakhs of people or 20 lakhs, some number of patients have been treated in the last 50 years using this proton therapy. Out of which one third is using the IBA machine. That's what they have written.
Good afternoon, sir. Good afternoon, sir. This is Dhanvi. Sir, my doubt is for application of nuclear radiation in healthcare. So we use X-rays also, like high energy X-rays from medical linear accelerator.
Yes, correct.
So how that being used for the cancer treatment? Sir, can you please elaborate?
See, as I showed you, most of the treatment for cancer has been using X-rays or cobalt gamma rays. If the cancer is located close to the skin or not very deep, this proton therapy, which is a sort of thing which has come in the country recently, is best when you have cancer or tumor located deep inside, a few centimeters below the skin. So otherwise, the ion edge X-rays, well, I told you, the damage takes place more in the beginning, and then it keeps on decreasing because there is an attenuation of the intensity. So depending upon the where the problem is, you can use an electron accelerator, which gives you again X-rays or cobalt 60 gamma rays. So you can either use the radioactive source or an electron accelerator. The advantage is if it is a radioactive source, it will be there all the time. Whereas if it is accelerator, you can switch on and switch off. That's why if you have a choice, accelerator is preferable. Of course, it is costly.
Thank you.
Yes.
So what are some common defects that can occur in food or radiation exposure?
Okay. Or you are saying due to radiation exposure. If you are getting exposed to radiation, what will happen? No, again, there are different levels. If it is up to certain level, then you will not find any problem with that person. If it keeps on exceeding, there is a level. If the person, of course, your blood they will take, and they will look for chromosomal aberration. How much it has got affected. So there are two things. One is radiation exposure. Other is somebody working by mistake. He has inhaled some, like plutonium in the form of, even a small amount. If you inhale, it will go and settle in your lungs, and it will continue to emit alpha particles, and it cannot be removed. That is one type of problem working in a radiation area. Other thing is exposed to radiation. Of course, first of all, we have radiation monitors everywhere, so that the person will not be able to go anywhere he likes. But accidentally, as it happened many years ago in Delhi and other places, somebody put a radioactive source in the market somewhere, selling old materials and all that. Then you just take one cylinder thinking it is nothing, but it contains radioactive substance. So you will have, after all, radioactive thing is like a heat source. It will also burn, and if the source strength is very large, then you will have a damage of the skin. If it is different levels, they will check the blood and find out how much of this aberration has taken place. Of course, whatever has happened has happened. You cannot do anything about it once it has happened. But what is the best is to prevent from that happening. That's why whenever people work in area, they have wear gloves, if required mask, everything is done so that you don't even accidentally touch it.
Hello, sir.
Yeah.
Yes.
Yes.
Thank you, sir, for the talk. I just wanted to ask about the slow and fast neutrons which you mentioned.
Yeah.
I didn't get it.
No, see, neutrons can be of different energies or different velocities. The slow neutron will take lot of time to go through, right? Velocity will be less. Fast neutrons will go very fast. Anyway, that is slow and fast.
What about the applications of it?
No, so what I said, these different neutron energies, when they interact with medium containing different elements, the nuclear process is different. If it is slow neutrons, whenever neutrons hit, say, carbon, they will interact and produce gamma rays with a higher probability if it is slow neutron. If it is fast neutron, it will do more of inelastic scattering and emit gamma rays, which is of a different amount, or I'm sorry, different energy. So slow neutron will emit gamma ray, neutron will be captured by carbon, and the carbon 13 will be formed, that will de-excite emitting a gamma ray. That is slow neutron. Fast neutrons will not do this. That probability of this will be less when you increase the energy. So we have both. So you have flexibility, different energies are for different applications. Yes.
So we in the medical field have something called as full body irradiation, where we use radioisotopes
Yeah.
to completely irradiate all the cancerous cells and cancerous tumors in the body. Now the down effect of this is that all our immune system is also completely irradiated and non-functional. So is there a way using nuclear energy or nuclear techniques can we have specific targeted therapies for this?
Let us see, all this treatment are no, they are all targeted only. You cannot expose the humans to all over the body, no. So first you have to identify the location, pinpoint that. So a lot of time goes in locating that, and then you use, microbeam and things like that to really hit only the. But the only thing is, you cannot say it is 100%. Some cells, good ones also will get affected, but that you should minimize. Okay, I think they may be hungry also. Thank you for your patience and asking some questions.
Thank you, sir. Thank you very much sir, for this enlightening and engaging session. Just to add, sir is also my mentor, I should say, because when I did PhD, sir was also a co-guide for me. He was guiding me throughout my career. I did my PhD at NPD BRC under Professor Kailas. Thank you, sir. As a token of appreciation, I'd like to call upon Srikanth sir to felicitate our IPA members, Dr. Vivek Parker. Dr. Pitamaha. Yes, as I mentioned, as a token of appreciation, we are Swamiji's book. Mr. Raman, sir. Sir, one minute. Madam, please. I request Principal Madam to, as a token of appreciation, to give a momentum to Gupta sir. I request Santosh sir, as a token of appreciation, to give a book to Lata ma'am and Sir please come. Santosh sir. Satin, please. Thank you, sir. So we have come to the end of this today's lecture seminar. Uh, we are very thankful to our principal madam and management for extending support to organize this event. Thank you, ma'am. Now, there are many teachers, students, and members who have worked behind this small event. So, we would like to thank Nitin for being a part or for organizing this online session. Yeah, and then we thank, actually, we should thank Dr. Bala sir. He's not present here, but he has arranged all the mementos and everything for us. We thank Vice Principal Madam also, all the students who have come here. Amit, Pradeep, they are our staff. They are not seen here, but they are all behind working, arranging lunch for you outside. And I just complete our team, department team, Principal Madam. Sir, you have, sir, please come. Dr. Devidas Bilbade sir, our in charge HOD, myself, Sarla Rathi, Shrikant sir, Santosh sir. Actually, all have worked hard, really worked hard to make this event a successful event. And I request you all, students, please come here. We'll have a group photograph and then you can depart for lunch, which is kept outside. Thank you very much. Food is arranged in first floor. Please do have your lunch and you can have an interaction session.